Section 4.3 starts out with a problem with this from The Simpsons. In fact, my son just took the SAT a little while ago, so this one feels really appropriate. It says, an episode of The Simpsons television show, Homer reads from a newspaper and announces, "Here's good news. According to this eye-catching article, SAT scores are declining at a slower rate." It means they're still going down, but they're going down at a slower rate. It says, interpret Homer's statement in terms of a function and its first and second derivatives. Well, the latter part we're going to get to, but let me give you two alternatives. And there's somebody asked a question like this in class earlier today. So, got a couple different functions, and let's see. I'll draw one like this, or another one like this. Which one looks like it's slowing at a slower rate? The green one or the pink one? The green one. So they're both decreasing still, but this one is going to decrease faster and this one's going to decrease slower. Now, the big difference in this is something called the concavity. This is a function that's concave up. This is a function that's concave down. And those are some of the things we're going to learn in this section, is how to tell what the concavity of something is and be able to apply that with our graphs. So that's just kind of a little heads up to where we're going. And let's see. But let's look back at the mean value theorem. We just finished section 4.2, which was the mean value theorem. And from the mean value theorem, we got that f prime of c is the secant line, the slope of the secant line for some point between a and b. That's what the mean value theorem says. But we get so much more out of this. Now, the mean value theorem is applying to functions along the x-axis, and a and b are assumed to be in this order. So that means b minus a is going to be positive. So, okay, if this is positive, then one of two things is happening with your continuous functions. If it's an increasing function, then this would be positive, right? Increasing function means as I move to the right that my function is getting taller, so that on the y-axis, f of a and f of b stack up like this. And when I subtract them, the larger minus the smaller is going to be positive. And essentially what this is saying is that if you have an increasing function, then the first derivative is going to be positive over that interval where the function's increasing. Now that's on your handout. It's on your little summary here. If y prime is greater than 0 on an interval, then the function is increasing on that interval. That's cool to know. That's handy to know. So to figure out what happens with a function, we can just look at its derivative. Likewise, if we play this game with a decreasing function, then what you'd find out with a decreasing function is that if the derivative is less than 0, the function has to be decreasing on that interval. Now there is kind of an in-between the case, or the in-between case. If y prime is 0, then a couple things could be happening. You could have a minimum, maximum, or an inflection point. And we'll learn what inflection points mean soon enough. Okay, but let's look at problem number 6 to begin with. Simpsons Rule? No. There actually is a Simpsons Rule, nothing at all related to Homer that we just dealt with, but there is a Simpsons Rule for calculus. Simpsons Rule, we actually have to learn some more things before I could discuss what Simpsons Rule is. So, okay. So, on what intervals is the function, the graph of the derivative of the function is shown here. On what intervals is the function increasing or decreasing? So we got to be kind of careful here, because they're not giving us the function, right? They're giving us the derivative of the function. So we've got to be thoughtful in thinking about this. What is it about the function, the derivative function, that tells us where it's increasing or decreasing? If it's positive or negative. So the way I see it, on the interval 0 to 1, the derivative is positive. So what's that saying about the function in the interval from 0 to 1? It's increasing. And we know that just by looking at the graph. So from 0 to 1, it's increasing. Where else is the function increasing? Nick? Yeah, 5 to 7. Good. So between 0 and 1 and between 5 and 7, the function is increasing. So let's write that down. So problem 6, increasing on 0 to 1 and 5 to 7. Now I'm using parentheses here, because at the endpoints, the function is kind of neither increasing or decreasing. Decreasing, well, it's going to be decreasing kind of everywhere else, right? So looking back, that would be the interval between 1 and 5. So between 1 and 5, and what else? 7 to 8. So yes, please.
On that graph that you were just showing.
Okay, yeah, so on the graph.
So if you look at the graph, where it's going, like, kind of going back up, but it's still in the negative, is that when it's, like, slowing down?
That's a good question. So it's hard to tell here if it would be slowing down. I don't think so, because if it was slowing down, then I would expect this to be kind of like curving and skimming the x-axis as opposed to diving right through it. So I don't think it's really slowing down there much. It just turns around real quickly and it starts going the other direction. So it's increasing, hits a maximum, then starts decreasing. So, all right, but good question. Let's take a look at another one. Problem number 10. And actually, I think I've got 10 lined up for us on your handout, right? All right, so let's take advantage of that. Problem 10 gives us this function. F of x is 2x cubed minus 9x squared plus 12x minus 3. And I want to know a few things from this function. I want to know where the function is increasing and decreasing. And that'll actually tell us a little bit more than just where it's increasing and decreasing. It tells us a little bit about minimums and maximums. So we'll first start by finding f prime of x. Go ahead and give it a shot. What's f prime of x equal? All right, so a few of you got that already. 6x squared minus 18x plus 12. And let's note for ourselves that we can factor out the 6, x squared minus 3x plus 2, and that eventually factors as x minus 2 times x minus 1. All right, it's good to have that factored. Bless you. Now, as far as finding the second derivative, I wouldn't use this. I'd go back to this form right here. What would be the problem of trying to find the derivative with this form of f prime? Yeah, I'd have to use a product rule. Yeah. And I don't think I see a lot of enthusiasm for that. So let's go back here. We'll keep it simple. F double prime of x is going to be 12x minus 18. Okay. Answer. You should get the same answer either way. If you differentiate here or here, you'd have to use a product rule and be a pain. So now let's take advantage of our handout. Try and make life easier for us. There's a couple interesting points on this graph, and that are points where the derivative is 0. So where is the derivative 0? 2 and 1. So x equals 2 and 1. And let's put those points right here in our little chart. So 1 and 2. Now I know that the derivative is 0 at these points, so I can fill that in as well. And what else? Well, I can plug in the value of x equal 1 into this function. So f of 1 would end up being 2. And f of 2 would be, likewise, it'd be 1. Like that. But let's put this into, let's see, we'll put the derivative into our calculator. Not the function, but the derivative. So hit the y equals key. We'll clear out the function. Yeah, we're just going to put the first derivative in for the moment. So it's going to be 6x squared minus 18x plus 12. And what I need from this is I need to know what's happening on either side. What's happening with the derivative? Is it positive here? Is it negative? What's going on? So what we'll do is we'll test points around these critical points. How are we going to do that? Well, with a table. Second, and then the graph key takes us to our table. Let's delete these. What would be a point somewhat to the left of 1? 0? Sure. Let's do 0. How about between 1 and 2? 1.5. Cool. And something to the right of 2. 3. Now, the important thing to get here is not the actual values. That's not what I'm after. What I'm after is the sign. I want to know, is it positive or negative? Now, why do I want just the sign? What does the positive or negative tell me? Increasing or decreasing. So let's take a look here. It was positive, negative, positive. So let's fill that in here. Positive, negative, positive. So that means the function is increasing. Let's put a little arrow there. This arrow is telling us the behavior of our function here. Between 1 and 2. Decreasing. And then increasing. Wow. That's telling you the shape of your function, isn't it? In fact, if a function is increasing, and then have a 0 derivative, then starts decreasing, what does it tell you about this point at x equal 1? What does it have to be? It has to be a local max. And if you look at your graph right here, you see exactly what's happening. The function is increasing, and has a derivative of 0, then it starts decreasing. So this is a local maximum. It's local max. How about over here? The function is decreasing, then it turns around and starts increasing. So what's going to happen here? Local min. And you can see that on the graph. You can see that on your graphing calculator. You've got a local minimum here. Wow. That's kind of cool. But there's a little bit more that I can get from this graph here. There's kind of a change in shape somewhere along the line. The function went from concave down to concave up. It changed from a shape that concave up is, roughly speaking, and I do mean this roughly speaking, a shape that'll hold water, and this is a shape that spills water. Concave down, concave up. So the question is, where's the transition point? Where does the function change its shape? Change from concave down to concave up. Well, that depends on the second derivative. So the second derivative tells you where the function's concave up and concave down. And I'm not going to try and derive that like I did with our first derivative. So concave up, that shape for this graph would be to the left of this point. It's concave up. And between these 2 points, it's concave down. And then the next 2 points, concave up. And from here over, concave down. And what measures the shape of the function in that regard is the second derivative. If the second derivative is positive, then it has a concave up shape. If the second derivative is negative, it has a concave down shape. So, okay, wow. Let's see here. Our second derivative was 12x minus 18. F of x, or f double prime of x, is 12x minus 18. Now, it'll be handy to know where that's equal to 0. So that's going to be 12x equals 18, or x is 18 over 12, which is 3 halves. So that's our point of interest for the second derivative, 3 halves. At x equals 3 halves, the second derivative is 0. Okay. And I need to test some points. I need to know what's happening around this. Now, I don't think I'm going to program it in my graphing calculator. If I put in, say, a 1, f of 1 would be what? Be negative 6, right? And the important thing there is not that it's actually negative 6, it's just that it's negative. So it'd be negative here. How about to the right? What's a point to the right of 3 halves? 2. So if I put in a 2 here, I get 6. So this is telling me that it's concave down and concave up. It's telling me the exact shape. And that little transition takes place right here. So if I ask you for where the function's increasing and decreasing, concave up and concave down, your answer is going to be intervals along the x-axis. So let's do with concave first. So concave up will be to the right of 3 halves. So it's going to be from 3 halves to infinity. And concave down is going to be everything up to 3 halves. So up to 3 halves would be negative infinity to 3 halves. That's where your function is concave down. When I'm asking you for this kind of information, it's always going to be intervals along the x-axis. So there to there for your concave down, and here to here for concave up. That's your concave up. Likewise, I can also ask you where a function's increasing and decreasing. Those are again going to be answers along the x-axis. So it's increasing until it gets to this local maximum at 1. So increasing from negative infinity to 1. Where else is it increasing? From 2 to infinity. Union 2 to infinity. And then decreasing, just from 1 to 2. So the derivative tells us a lot about the shape of a graph. First derivative tells us where it's increasing and decreasing. Second derivative tells us if it's concave up or concave down. Okay. Any thoughts on problem number 10 here? We're going to do a few more like that. Okay, let's see what else we have in our handouts. All right, take the easy path through this stuff. And I think the next one's going to be problem number 14. Yeah, how about that? I got you all set up for problem number 14. Let's see, problem 14. F of x is cosine squared of x minus 2x, or excuse me, 2 sine of x. Rats. 2 sine of x. And let's limit ourselves to between 0 and 2 pi. So we'll just make that restriction 0 to 2 pi. It's important when you look at this and differentiate this to realize that that's really cosine of x squared minus 2 sine of x. And we got to work hard with the derivative. So the derivative is going to be the derivative of the outside, 2 cosine of x times the derivative of the inside. What's the derivative of the inside? Negative sine of x minus 2 cosine of x. So if I clean this one up, it's going to be minus 2 cosine of x sine of x minus 2 cosine of x. All right, so that's f prime. Here we go, f prime of x. Well, I need to know where this is equal to 0. And that's a little bit of a pain. Equal to 0. I'll factor out the negative 2 cosine of x. Bless you. And that leaves behind what? Let's see, sine of x plus 1. So we got a couple possibilities here. Let's work on both of them. So I have something times something equals 0. One of those somethings has to be 0. Either cosine of x is 0 or sine of x plus 1 is 0. One of those two has to be true. So where does cosine of x equal 0? Well, cosine is which coordinate on your unit circle? X coordinate. So where's the x coordinate equal to 0? So the x-coordinate is going to equal 0 here and here. So at pi over 2 and 3 pi over 2. Please don't use 90 and 270. Calculus is done in radians. So pi over 2 and 3 pi over 2. Okay. Let's look at the sine of x plus 1 equals 0, which is sine of x equal negative 1. Where is that true? Sine is which coordinate? The y-coordinate. All right, so sine is the y-coordinate. I'm looking for the y-coordinate to be negative 1. 3 pi over 2 again. So, okay, well, I get that one twice. No big deal. But those are our two critical points. So pi over 2 and 3 pi over 2. So let's put those in there. Now, the second derivative is a lot more work. You got to use the product rule. You also eventually got to use the idea that sine squared plus cosine squared equals 1, and then make a substitution. I forget which way. Let's see. You have to make a substitution of cosine squared of x equals 1 minus sine squared of x. And working with that, you can eventually get this expression for the second derivative. F double prime of x is 4 sine squared of x plus 2 sine of x minus 2. Now, if you factor out the 2, that's what I got here, F double prime. Oh, on the handout, all right, thank you. Yeah, this should be F double prime. Thank you. So, if you factor out the 2, the rest of it can factor as 2 times 2 sine of x minus 1 times sine of x plus 1. And kind of like the previous part, I want to know where that's equal to 0. So this is going to equal 0. Well, we already know what that's true right here, right? We just solved that. X equals 3 pi over 2. But how about this one? Where does 2 sine of x minus 1 equal 0? Sine of x equals 1/2. Sine is your y-coordinate, right? So think about the unit circle. Now, your calculator can help you out if you're lost, if you don't have a unit circle around. You can always do the inverse sine of 1/2. I'd probably have my calculator in radian or degree mode if I did that. The inverse sine of 0.5 is 30 degrees, but that's pi over 6. We're looking for the y-coordinate. So not pi over 6 and 11 pi over 6, that would be the x-coordinate. Pi over 6 and 5 pi over 6. Those are the two places that have a y-coordinate of 1/2 for sine. 5 pi over 6 and pi over 6. So I got those 3 points. Bless you. Let's put them on our little chart here. Pi over 6, 5 pi over 6, and 3 pi over 2. Okay. Nice. We got a lot of testing to do here. We know that the derivative here and here is 0. Likewise with the second derivative. I guess the hard part about this is knowing what decimal values these would be, really. It's understanding, like, well, what is that? This is about 1.57. This is about 4.71. And so if you plug in the derivative, then you can choose some test points appropriately. All right. Maybe we should practice with just one of these. So let's plug in the derivative, which was this expression right here. Let's plug it in. Put your calculator in radian mode. So, I've never really tried it. I don't know if your graphing calculator understands this notation. So I'm going to put it in with parentheses. Actually, you know what? I don't need to for this one, do I? It's going to be -2. Let's see, -2 cosine of x, sine of x, cosine of x, sine of x. I need a parenthesis there. Sine of x minus 2 sine of x. No, 2 cosine of x. So there's our derivative. Let's go to the table, second, and then table. I'll get rid of these old values here. And now I need some test points. And here's why we gave ourselves some decimal values. It's just to know roughly where we can test. What would be a point to the left of pi over 2? 1. And between these two? 2, sure. And then to the right of 3 pi over 2. I did 12, didn't I? 1. Thanks, Guy. 2. And I need one more. 5. So positive, negative, positive. That's what this is telling me. No, excuse me, the other way around, yeah. Negative, positive, negative. Thank you. Negative, positive, negative. What's that saying about the graph? Decreasing, increasing, decreasing. Okay, that's nice. Now, if something is decreasing and then starts increasing, I mean, look at this. It's drawing the graph for you right here. What kind of a point do I have at pi over 2? Local min. All right, so I got a local min there. Increasing to decreasing suggests a local max. All right, and our graph down here confirms that. Local min, local max. All right, I'm going to help us out with the second part of this in terms of the testing. And the testing has kind of an interesting pattern here. It's, I don't trust that. These last two were negative, negative, negative. Yeah, positive, negative. Yeah, okay. I go with that. So here's the sign of the second derivative. You tell me what that means here. Like we did here, this was decreasing, increasing, decreasing. What does it mean that the second derivative is negative, positive, negative, negative? Concave down, concave up, concave down, and concave down again. So that's interesting. Now, the one point that I wouldn't pick up on, and this is why you have to use the calculus, is that until we get to about pi over 6, which is probably here, I'm guessing, until we get to this point, this is actually concave down. Boy, it doesn't look like it, does it? You'd have to look really hard and look really hard again to see that that's concave down. But we know it's concave down because the second derivative is negative there. So it's concave down. And then it's concave up until I get to 5 pi over 6, which, again, I'm guessing it's about here. So in this interval, it's concave up. And then it's concave down. And it's concave down again, which is kind of unusual behavior. It's concave down on twice this. It does pause right here. And for a brief moment, the second derivative was 0. But notice what that does to the graph. It gives you a very flat graph, saying, all right, the second derivative flattened out, so that's why you're getting this odd behavior where the function looks like it's almost level for a little bit. It's not, but it looks that way. Let's put this all together as a final answer. In terms of increasing, functions increasing from pi over 2 to 3 pi over 2. That makes sense. That's this interval right here. So pi over 2 to 3 pi over 2. And it's decreasing, well, from 0 to pi over 2. Union 3 pi over 2 to 2 pi over 2. Or excuse me, 2 pi. 3 pi over 2 to 2 pi. That's where it's decreasing. What else? Well, we need to talk about the concavity. Concave up, that's the easy part. That's just simply between pi over 6 and 5 pi over 6. Pi over 6 to 5 pi over 6. It's concave down pretty much everywhere else. And I'm just going to list them. It's concave down from 0 to pi over 6, union 5 pi over 6 to 3 pi over 2, union 3 pi over 2 to 2 pi. I'm not really comfortable with going from, say, 5 pi over 6 to 2 pi because there's a brief moment where it's neither concave up nor not concave. It's neither concave up nor down. So I probably wouldn't like you to list it from here to here. If you just said maybe accept 3 pi over 2, that'd be fine. But again, it's a matter of testing points here, positive or negative. Okay. Seems to match everything here in terms of our graph. I think the hard part here for us would be to set the derivative equal to 0 and solve, especially working with the second derivative and solving. Hopefully the little extra help that I gave you makes it a little bit more digestible. So I want to have a follow-up on this one. Wow. Someone run out and get a case of 5-hour energy for us. All right. Okay. Let's look at problem number 22. Problem 22 is kind of amusing, especially if you try and graph it. Ultimately, you should be able to understand some of these things, not without necessarily always relying on the graphing calculator. I mean, the graphing calculator is wonderful, so is Desmos, but we do need to be able to do things outside of that. But they're helpful, and we'll continue to use it. Now, one of the things that we've been finding here is local mins and local maxes. So you have a local min if you go from negative to positive across a critical point. You have a local max if you go the other way, from positive to negative across a critical point. So that's called your first derivative test. It's on one of your handouts. First derivative test. So suppose C is a critical number and you have a continuous function. So if the derivative goes from negative to positive, so decreasing to positive, decreasing to increasing, then you've got a minimum point as your critical point. If it's the other way around, if the derivative goes from positive to negative, then you've got a maximum point because you have a behavior like this, increasing to decreasing. So that's the first derivative test. And that's a nice way to tell whether or not something's a maximum. Quite often you want to maximize functions. But there's another way you can tell where, if something's a maximum. If you have a critical number, a critical point in a function, then all you have to do is plug it in the second derivative. If the second derivative is less than 0, well, what's the shape at that point? If the second derivative is less than 0, then you have a concave down shape. So that would mean that your critical number would be a maximum. If you have a concave up shape, then your critical number has to be a minimum. So it's a different way to decide whether or not you've got a minimum or maximum at a particular point. So let's apply that to problem number 22. And I think 22 will be the last one for today. So if you're feeling a little lack of energy, my apologies. Second derivative. Test. All right, second derivative test. So problem number 22 gives us f of x equals x to the fourth times x minus 1 cubed. Well, let's see here. Let's work on finding the first derivative. F prime of x. What do I have to do to find the first derivative? Product rule. Yeah, you got to use a product rule. So, the chain rule a little bit. Although, yeah, you're going to have the derivative of the inside here is going to be 1, so it's not going to be that big of a deal. So, derivative of the first would be our 4x cubed times the second plus the derivative of the second. Let's do that. 3 times x minus 1 squared. Let's see, I need a cube here still. Times x to the fourth. Well, the derivative of the inside here is 1. And times x to the fourth. I can't say this strongly enough. You got to clean this one up. We're not going to be able to find where this equals 0 unless we clean this up. So let's look at it this way. There's a greatest common factor here, right? What's the GCF? X minus 1 squared. What else can I factor out? So x to the third times x minus 1 squared. Let's put brackets here. Now if I factor that all out, what's left behind? 4 times x minus 1 plus, the 3 is still there, and one of the x's, so plus 3x. So, okay. And I can combine like terms here, right? If I distribute that, that's 4x plus 3x gives me 7x. So x cubed times x minus 1 squared times 7x minus 4. Yay. All right. Why did I need to do all that? Well, because I need to know where this could equal 0. I need to know the critical values. So, okay. Where could this equal 0? I'm hoping that you could read this off. X could be 0, 1, or 4/7. Now that last one, I mean, you might get the first two, by looking at this a little bit, but you're certainly not going to get the last one very easily. That one's a tough sell. So that's why you need to be able to factor these things and clean them up. Okay. Let's see. The second derivative, I'm just going to give you the second derivative because the second derivative is kind of a pain. But before, let's see. Question? Okay. Give it to on the handout. No, not there. There we go. Let's see here. Let's make ourselves a little table. Well, I didn't mean to do that. Let's see, x, f, f prime, and then I'm going to plug in values for 0, 1, and 4/7. 0, 1, and 4/7. Now I know the derivative is 0 in all these points. We just calculated those. Those are our critical points. I need to test the sign of the derivative in between all these points. So, okay, well, let's do that. So I'm going to plug in the derivative into my function in my calculator and test points on either side of all these critical points. Let's see. So we'll do x raised to the third times x minus 1 squared times 4x minus, or 7x minus 4. One thing that makes me feel comfortable, if you calculated what degree this would be, I've got 3, 2, and 1, that's 6. I started out with a 7th degree polynomial. When you differentiate something of degree 7, you're going to get degree 6. So that's looking good. At least I feel confident in that respect. I need some test points. I can't use 0. Let's use -1. And then 0.5 between these. And you know what? I screwed up, didn't I? Yeah, I got these backwards. Got to have these things in order. So this should be 4/7, and then 1. Now 4/7 is probably what, about 0.58 or something like that? Okay. So I think I'm okay. So I've got, let's see, -1. The function's positive here. And then at 0.5, 0.5 is between these two because this is 0.57. So 0.5, we're good there. The function is negative. And then let's do, say, 0.75. Derivative is positive. And then to the right of 1, we'll just pick 2. Positive again. Not trusting something. Oh, let me just delete here. So positive, negative, positive. Let's do 1.1. Still positive. Both positive. Oh, that's a good question. Yeah, I forgot about that. -1 to 1. So we don't need to worry about that. But let's take a look at these points. What's the first derivative test telling us about a point like this? What's it saying about the point at 0? Increasing and then decreasing. I'm hoping that this just spells out the shape for us. This is a local what? Max. And this is a local min. Now this is all part of what's, what I started out with is to demonstrate the second derivative test. And the second derivative is a real pain. So that's why I gave it to you on your handout. Second derivative looks like this here. And according to second derivative test, second derivative test says, all right, if you have a critical point, then it's a minimum. If the second derivative is greater than 0, it's a maximum. If it's less than 0. But what it doesn't say is what if f double prime of c equals 0. And if f double prime of c equals 0, then the test is inconclusive. Now, a lot of times you'll find the second derivative test to be easier than the first derivative test, or useful in conjunction with the first derivative test. But unfortunately for us, if you try to find f double prime of 0, if you put in a 0 here, you get 0. If you put in f double prime of 1, you'd also get a 0, right? If you put in f double prime of 4/7, you get some crazy decimal value, which I think is positive. Let's see, where's my notes here on this one? Yeah, it's about 0.2399. Doesn't matter exactly what it is. It's greater than 0. So the only thing that the second derivative test works for in this case is this one. And if this is greater than 0, this is a minimum point. Okay, I'm going to stop here. We'll have to do a little bit more in this section later.